All right, welcome back to Asymptotics and Perturbation Methods. We've been talking about boundary layer theory, and we will continue to for another few lectures. Where we got to was some methods for calculating what's happening in the inner region and the outer region, matching them together. But one thing that we left open was the question of where are the boundary layers? How do we know where they occur? Which boundary will they be at? Could they be in the middle of the region somewhere? So we're going to start talking about issues like that. Today, we're going to discuss how you can locate the boundary layer and also how thick is it? We've been assuming throughout that it scales proportional to the small parameter epsilon. So as epsilon goes to zero, the thickness of the boundary layer also shrinks in proportion to epsilon. But how do we know that that's true? And is it always true? Actually, it's not always true. You can have boundary layers of different thickness. They can scale sometimes like a power of epsilon that's not epsilon to the first. Sometimes they could even be logarithmic in epsilon. So we're going to address issues like that today too. All right, so let me get rolling. Here we go. Excuse me for 1 second. I'm going to see what's happening in the chat. Oh, okay, no problem. Some of my students are listening from noisy places on campus. That's the way it is in this era. Anyway, okay, so here we are. The question is the location and the thickness of boundary layers. This is addressed a little bit in the first section of chapter 9 in Bender and Orsag. In 9.1, they tell you something about how to locate the boundary layer, but really 9.4 is the section that you should be focused on. All right, so let's begin with one of our standard model linear problems, just as a warm-up, then we'll do something a little juicier. I have written it out partially ahead of time just to save some time here. So here's our question. We've got a differential equation, which we could solve exactly, but we're not going to. We're going to just pretend we can't, and we're going to approach it with boundary layer techniques. So we've got this epsilon y double prime, the small epsilon multiplying the highest derivative as typical in these boundary layer problems. Then some linear terms, minus y prime plus y equals 0. And I've got two boundary conditions. Y of 0 is 0, y of 1 is 1. All right, now, the first step is to find what we call the outer solution, where we just pretend, again, we're thinking of epsilon going to 0 from the positive side. So if we just pretend that first term, epsilon y double prime, is small, since it's got the epsilon in front of it, this term, and just ignore it, that leads us to the outer solution, which we can obtain by thinking about, we could actually just solve it explicitly, but suppose we do our usual perturbation move and say something like y outer. We're going to expand in a perturbation series as y0 plus epsilon, y1 plus, etc. So at that lowest order, the y0 equation will satisfy this, minus y0 prime plus y0 is 0. Go away. Which has its solution in terms of a growing exponential. Y equals a constant a times e to the x. That should already make you a little suspicious. Growing exponentials, we don't really expect that. In boundary layers, we usually think that something's going to decay exponentially as it moves away from the boundary layer. So this already is sort of suggestive of the boundary layer going to be at the right side of the interval at x equals 1, so that as we move back into the interval between 1 and 0, we'll be exponentially decaying away from x equals 1. So by that kind of common sense thinking, you might figure the boundary layer will be at x equals 1. Well, let's suppose we don't have any common sense just yet, and we're really truly mystified about which boundary condition to apply. Like we have no idea where the layer is going to be. So continuing in our foolish ways, let's suppose that the boundary layer is at x equals 0. That's going to be wrong. All right, that turns out to be wrong. Not very surprising, but I want to illustrate what it looks like when you're doing it wrong so that you'll be able to recognize when you're falling into such a trap. Okay, so just blithely proceeding with this assumption that the boundary layer is at x equals 0, then since we're interested in this outer solution and we think the boundary layer is at x equals 0, that would tell us we should be applying the boundary condition appropriate to the outer region, which would then be at x equals 1. X equals 0 would be the boundary condition for the inner region under this hypothesis of a layer at 0. So all right, so let's go ahead and do that. The boundary condition at x equals 1 tells us that y at 1 is 1. And since y, the lowest order, the solution is a e to the x, that's supposed to be 1. Applying that at x equals 1, you get a times e is 1. And so then solving for a, we get a is 1 over e. And I can then substitute that back in here for a, giving me 1 over e times e to the x, or e to the x minus 1. Okay, so that's what the outer solution would look like. Next, let's look at the inner solution, still under this, what's going to turn out to be wrong assumption that the boundary layer is at x equals 0. So now this part of the calculation is going to illustrate how do we estimate the thickness of the boundary layer when we don't know it a priori. So let's just assume it has some thickness that we're going to call of order delta, where we don't really know what delta is, just that it depends on epsilon somehow. And so this delta is to be determined. We have to figure out a way to calculate the thickness without solving the equation itself. So here's the kind of reasoning you could use. Even though this whole calculation is wrong-headed at this point, this part of it is correct. And we're going to use this reasoning later. So this really does work. So we're going to choose this inner variable, capital X, to be x divided by the characteristic thickness of the layer, delta. And so with that choice of units, or scaling, then that's going to make the big X variable of order 1 in the boundary layer, because we've now scaled things according to the correct thickness. Meaning as epsilon goes to 0, we can think of capital X as remaining fixed at any, say, one step, or, well, let me not keep talking about that. I mean, we've drawn this picture before where we're kind of laying at the axis in the boundary layer as 1, 2, 3, rather than 1 epsilon, 2 epsilon, 3 epsilon, or in this case, 1 delta, 2 delta, 3 delta. Okay, anyway, so there's our X, capital X variable. And then we're going to write the inner solution in terms of that big X variable, now call it capital Y, just to help distinguish. And next, we got to rewrite the differential equation. But in doing that, maybe I should mention one little thing, which is that I've scaled the independent variable, big X, but why don't I scale the Y variable? There's no need to. The equation is linear. Remember, we started with a linear equation. If you go back here, this is linear in Y. So no matter what scalar I multiply Y by, it will just cancel out, right? I mean, yeah, if you got a linear operator times Y equals 0, then that same linear operator times C times Y is going to be 0. So the C will just drop out. There's no point trying to scale it. The one thing you could observe is that since the equation is linear, we do have scales on the boundary conditions, though. We said that Y of 1 was 1. So that says that the scale for the boundary condition is 1, and since the whole equation is linear, you'd sort of expect little y to have an order 1 scale throughout. So that's what we're going to assume. Hope that reasoning made sense. Okay, we will see some nonlinear problems later in the course where we have to scale both x and y. That'll be coming up soon. There are even some linear problems where that's relevant, as we'll see in the next lecture. So, but for now, we're in the simple setting where we don't have to scale y. All right, so with these ideas in mind, we're going to transform the differential equation into the new capital X variable. So y prime, which means dy dx, using the chain rule, is d big Y d big X times d big X d little x. And from the definition of big X, this derivative is just 1 over delta. So our transformed derivative is 1 over delta times y sub dimensionless x, so to speak, capital X. Similarly, when we take two derivatives, we'll get two factors of delta down there, so 1 over delta squared. We've seen this kind of thing before. We saw it in the last lecture just with epsilon in place of delta. So our ordinary differential equation is now what we see in the box, and that's as far as I wrote out ahead of time. So is there any questions so far? We haven't yet determined delta, but we're going to do that now. Anyone want to jump in with anything? Okay. All right, so there we are now. At this stage, the kind of argument that we're going to make is a dominant balance argument. We did this earlier in the course when we were solving equations asymptotically at large x or small x. Similar here, except that we're now going to do dominant balance on the parameters. Things like this term, the epsilon over delta squared, or the 1 over delta, or the prefactor of 1 that's invisibly multiplying this capital Y. And because we're assuming that the big Y is all of order 1, and its derivatives as well. If we've chosen the scales correctly in x, Y and its derivatives should be order 1. That's what it means to have captured the rapid variation in the layer. When the delta is chosen correctly, it will be the case that Y and its derivatives are order 1. This will be true if delta is chosen correctly. So since those quantities are not big, we don't have to think about them in terms of the dominant balance. And what we do is then write out what is the dominant balance as epsilon goes to 0. Is it, for instance, that epsilon over delta squared is comparable to 1 over delta, but both of them are much greater than 1 as epsilon goes to 0. That's one possibility. So let's call that possibility A. I mean, could that be the case? So if that were true, well, let's see. I mean, as we unwind it, solve for delta in terms of epsilon, you see that this is saying that delta would then be sort of the same order of magnitude as epsilon, and also that delta, both of them would be much less than 1. So that's all consistent. I mean, that can work because we know that delta and epsilon are much smaller than 1. So this all looks reasonable. By the way, why am I writing the double squiggles? I'm just trying to say, like, you can interpret this to mean delta equals big O of epsilon, where I'm not worrying about the prefactor. I'm just saying that it scales at the same as epsilon to the first power as epsilon goes to 0. I don't care about the constant in front of that. So I don't want to write a single squiggle because that would mean that the prefactor is 1. Right? It's not saying delta is asymptotic to epsilon. It's just scaling like epsilon. So I'm going to write that with 2 squiggles. All right, so this is one possibility. Now let's consider other possible balances. Another possibility would be epsilon over delta squared being the big term, balanced by, say, the order. I mean, here I'm now saying, suppose this term is balanced by this 1 sitting here, and that both of them are much bigger than 1 over delta. If you try that, well, solving the first approximate equality would say that delta is then approximately epsilon to the half, but we know epsilon is going to 0, so this is much less than 1, whereas this equation says delta is much greater than 1. So those are inconsistent, right? That cannot be a correct. Those contradict each other. So that's not right. And then the final possibility is, well, what if, again, looking at the equation, what if we had 1 over delta balancing against 1, but both of them are much bigger than epsilon over delta squared? So that would be 1 over delta balancing 1, but much greater than epsilon over delta squared. So if we did that, that would be saying from the first approximate equality that delta is of order 1 and that epsilon is much less than 1. Now that's okay. That is reasonable. Epsilon is much less than 1, but saying delta is approximately 1 means you're talking about the outer solution, not the inner solution. A scale of delta being 1 is what's happening in the outer region, not in the layer. So what you've just done here is recovered the outer solution, and we're not interested in that at the moment. So this is the scaling for the outer solution. So we've already talked about that. And so B and C are ruled out for that reason. And so we really want to focus on case A, which is that the boundary layer has thickness proportional to epsilon, would be the conclusion from this part of the argument. So I'm going to be writing boundary layer so often, let me just use the abbreviation BL. Has a thickness of delta that scales like epsilon. Right, so that's the reasoning on this. So that's typical of the arguments we would use to figure out a thickness. Funny thing about this part of the argument is that this is all predicated on assuming that the boundary layer is at a place that it is not. Nevertheless, this part of the reasoning is correct. It's just the earlier part is wrong, as we'll see momentarily. So how are we going to tell that it's wrong? It's going to be because we can't match the inner and outer solutions. That's the signal that we've done something wrong. Matching becomes impossible. So we're going to see that in a minute. But I just want to introduce some jargon, because when you're reading Bender and Orsag, you'll run into this phrase. This kind of argument that we did here, where only one of the balances was possible, they call a distinguished limit. I don't know that I'll be using that phrase too much, but the distinguished limit is where we have the only case that gives a non-trivial balance. So it gives a consistent and non-trivial balance. By trivial here, what I'm saying is I don't want the outer solution again. The outer solution is consistent, but trivial in the sense that it's not helping us deal with the inner solution. Okay, so anyway, we've just worked out the distinguished limit. And so we got that scaling. Now, what does that do for us? So we're going to let our inner variable just be x over epsilon. That is, we're choosing delta equals epsilon. And so with that choice, then the inner equation becomes, let's go back to it. Where was it? It was written up here in this box. setting epsilon, I mean, since I'm choosing delta equals epsilon, when you multiply everything through in this equation in the box, you'll end up getting yxx minus y single x plus epsilon big Y equals 0. That's my inner equation. And remember, we're still making this wrong-headed assumption that the boundary layer is at 0. So we want to impose the boundary condition at 0, which was that y of 0 is 0. And so that's our inner problem. This stuff. And as you can see, it's a second order equation. We only have one boundary condition. We're going to get one arbitrary constant, and that'll be determined by matching if we could do matching. So let's see here. We're going to write an ansatz for y as y0 plus epsilon y1 plus et cetera. And plugging that in, you get at lowest order that y0 sub xx minus y0 sub x is 0. You know, not surprisingly, if you just look at this equation, that's the equation you get when epsilon is 0. And the boundary condition on the lowest order term is y0 of 0 is 0. Okay, so there's our inner problem. And now let's solve it. Okay, I mean, so you have to integrate twice. You end up getting y0 of x. When you integrate this little differential equation, comes out to be, and applying the boundary condition, I'll skip those steps. You get a constant, call it b, times 1 minus e to the x. All right, so there's the b, and the b is to be determined by matching, but now we get into trouble. I mean, this is already very suspicious, right? This is exponentially growing away from x equals 0, where we thought the boundary layer was. That's a sign of trouble. So as I mentioned earlier, this is a bad sign when this happens, because solutions usually decay I mean, you expect decaying away from the endpoint of the boundary layer. Not grow. Okay, so this is looking bad, and it is bad. If we try to match, watch what happens. Well, so what is the matching condition? We're supposed to look at the limit as big X goes to infinity, as we go far out to the outermost reaches of the layer of y0 of x. This is the primitive matching at 0th order. We would think this should be the limit as little x goes to 0 of the inner solution, sorry, of the outer solution, excuse me. Let's see, I see something in the chat. Is this a question or an apology or what? What would we do if 2 or more balances are possible, asks Maria. Good question. That will come up. We'll see situations. Actually, I think what we'll see is cases where it's not just 2 terms that balance, but more than 2. You can have 3 or more. Those lead to very interesting boundary layer equations. But if you had two or more that are both consistent, but not trivially consistent, that's interesting. I'm not sure I've run into a question like that. I'm not saying it's not possible. Wasn't planning to discuss that. I know there are circumstances where you can have a layer inside of a layer. So it's possible that what you're bringing up, Maria, might lead to that phenomenon. But honestly, I'm not sure, and I hesitate to say anything about it. So let's leave that question as a question, and we'll see if we can come back to that. You might look in Bender and Orsag in the next section of the book. In 9.5, they do several more advanced examples of boundary layer that I wasn't planning to cover and have not covered in the past and have not taught myself. So it could be that they have layer inside of layer in there doing what you're suggesting, but I'm not sure. Okay, but anyway, so let's try to do this match. You can see the problem that here I'm supposed to be looking at the limit as x goes to infinity of b, 1 minus e to the positive x. This is infinity. I mean, assuming b is not 0. Whereas, what is this limit? The limit of y out, I'm looking at the limit as x goes to 0 of, so what was that one? That was e to the x minus 1. That would just be e to the negative 1. There's nothing that can work, right? I mean, if b is non-zero, then we get infinity over here. And if b is 0, we get 0. And neither of those can match e to the minus 1. So there's no good way to make this work. Just the matching is impossible. So that's a sign that we had the boundary layer at the wrong place. We guessed the location. Of the boundary layer incorrectly. Okay, so yeah. Now let me do it the right way. But maybe first, any question then about, this wrong calculation that we spent so much time on? All right. So in fact, the boundary layer is at x equals 1, as we sort of suspected from the beginning. And so let's see, we can salvage some of our earlier work. It would still be true that y outer of x is of the form a e to the x. That's still true. But now the appropriate boundary condition, since we're thinking that the layer, since the outer region goes all the way back to x equals 0, now that we understand that, the appropriate boundary condition is that x equals 0, which you may recall was that y of 0 was 0. So this tells us that a e to the 0 should be 0, which implies that a itself is equal to 0. Which looks a little weird because that's telling us that y out of x, actually to all orders of perturbation theory, is just the identically 0 function. So fine, it looks a little bizarre, but that's what's happening in the outer region. Now, again, let's do the boundary layer thickness calculation to see what's happening in the inner region. Well, Now, what's the difference? We're thinking now that the boundary layer is at x equals 1. So the correct choice of big X is now you write it as, actually, we're sort of used to thinking of letting positive X go to infinity as we go from the beginning of the boundary layer out to the end of it. So I'm going to reverse orientation on the x-axis. Might seem a little weird to do that, but I think it's most natural. That is, I'm going to define x to be 1 minus little x, all divided by delta, where remember my x is running between 0 and 1. And so this makes the big X go from what? I guess from 0 to 1 over delta. But you should sort of think of that as infinity, because delta is going to be going to 0 as epsilon goes to 0. So the big X is running over basically an infinite region. All right, but anyway, let's calculate the little delta. Do the same thing as before. We assume y in as big Y of this big X. The same kinds of calculations will lead us to something that now looks like epsilon over delta squared, big Y sub 2x's plus 1 over delta y sub x plus y equals 0, which might remind you of the equation we had earlier, but it's a little bit different. See if we can see why. I mean, where's the difference? It actually comes right from this step. That when I calculate y sub x and change variables, when I do the move of writing d big Y, d big X, d big X, d little x. When I do this step, I get here y sub big X. But notice that because of this choice of variable, when I take d big X, d little x, I get a negative sign. I get times negative 1 over delta. And so that has the effect of causing that term to be positive. See, let's go back. What was the governing equation? Contrast that with what we had in the earlier inner problem. Notice we had a negative y sub x, right? Now we have a positive y sub x. And it makes a big difference because now we're going to get exponential decay in the boundary layer rather than exponential growth. I see a question here. Yeah. Oh, let's see. So the question again, this another from Maria was, is there any point before matching when we could have realized we were making a bad choice? Yeah, I mean, again, this idea that if you see that something's growing exponentially as you move deeper into the layer, that looks sketchy. Things should usually decay. The layer is a region of rapid variation, but usually it's rapid decay, not rapid growth. I mean, yeah, as you move away from the endpoint, things should be decaying, typically. So anyway, here we are. We've got this plus. You could use the same kind of balance argument. The distinguished limit, again, will turn out to be again, will be delta scales like epsilon. And so this will lead us to, so I'm skipping that step, but you could check it by the same type of argument we just did earlier. You would now get this layer equation. And so doing this at lowest order, y0, 2x's, plus y0, 1x, equals 0. That's my order 1 equation. And it has a solution, y0 of big X equals a constant, call it C, plus another constant D, and then with exponential decay, e to the minus x, which is looking good. And the condition on it, boundary condition, is y0 at the endpoint 0. Now, what is, so this is a little confusing. What is, why am I saying 0 there? Let me see, there's this funny choice of variables. Look at this again. The right-hand endpoint x equals 1 corresponds to big X equals 0. So that's why I'm imposing a condition on big X equals 0. This still means the right-hand endpoint. It's the right endpoint of the domain, you know, relative to the X, the little x. So two different names, but big X equals 0 is what we want to be imposing at this right endpoint. And so we're getting that this equals well, what? C plus D. But y sub 0 of 0 was supposed to be equal to 1. That was my boundary condition. That little x equals 1, right? It was y of 1 equals 1. So this whole thing is supposed to be 1. And so solving for, I don't know, let's eliminate D. You get D is 1 minus C. So big Y, 0 of big X is C plus 1 minus C e to the minus big X. And now let's try to do matching on that. So this is going to work. So the 0th order match condition is that the limit as big X goes to infinity, going out of the boundary layer into the overlap region that we talked about in previous lectures. This should equal the limit as little x goes to its right-hand endpoint, which is still called little x equals 1 of the outer solution. But remember, the outer solution was just identically 0. Whereas over here, maybe I'll do that on another page. I'll stay on the same page. What am I doing? So here I have to look at this expression, this equation up here, and take big X to infinity. This is going to give me C, because the e to the minus x term vanishes as x goes to infinity. So I'm led to the conclusion that C equals 0. And also this gives me my Y match as a function of X is this matched value of 0. So I'm ready now to do my composite solution trick, the uniform solution. I mean, notice we did succeed in matching. So we write Y composite is Y out plus Y in minus Y match. And so Y out, we said, was identically 0 plus Y in. When I substitute C equals 0, well, let's do this at lowest order. So Y out sub 0, that's just 0. The Y in sub 0, we just calculated up here. If I look at this with C equal to 0, I just get e to the minus big X. So this is e to the minus big X. And then minus Y match, which is 0. And now, remembering what is the definition of this big X, this is e to the 1 minus x over epsilon. Unless I've screwed that up, which I have. This should be a negative sign. So writing it a little more understandably, the leading order solution for the composite, let's try this again. So y composite as a function of x is coming out to be e to the x minus 1 over epsilon. Plus, I didn't go out to order epsilon correction terms and didn't bother with that. So there we are. That's our answer. Which, if you want to understand what that looks like qualitatively, the picture would be, I didn't draw this in Mathematica because it's a little too easy. I have a boundary layer over here at x equals 1, going up to a value of 1. And then the whole solution just decays exponentially, and then becomes practically 0 over here. So that's what this looks like. So this is my y composite of x. And this characteristic thickness is sort of order epsilon. But the thing that's funny, I mean, you might notice, there's a bunch of funny things in a way. This solution, the composite solution, is very small. Remember, it's trying to masquerade as something that wants to be identically 0, but it's not actually literally 0. And in fact, this solution does not satisfy the boundary condition at this end. It's supposed to be 0 over here, but it's not. It's just transcendentally small. But that sometimes happens. So our matched asymptotics do not give us something that actually satisfies the boundary value problem. It's getting the boundary condition a little bit wrong, but it's negligible. You wouldn't see it anything. If you graph the solution, you won't see a thing that looks wrong. Okay, so any question then about this calculation? This was supposed to show you how you estimate the thickness and also how you locate the boundary layer itself. All right, so that was example 1. Now, we don't want to do that kind of thing every time, and there are shortcuts. So let me tell you a very handy shortcut that works for linear problems. So let's suppose we're considering pretty general second order boundary value problem. Let's suppose it's linear but has variable coefficients. So for a second order boundary value problem of the form, epsilon y double prime plus some function a of x, y prime, plus another function b of x, y equals 0. So I don't know why I said general, because it's not so general. I'm making some big assumptions here. Let's suppose this is on the interval 0 to 1. So notice a few things. It's homogeneous, got a 0 on the right-hand side. It's also linear in y. Right, I mean, it's a linear equation. So maybe I should even put that in there. It's a second order linear boundary value problem of this form, homogeneous. Then what we can say something pretty nice. Suppose we have simple boundary conditions where I give you the value at both endpoints. So y of 0 is some constant a, y at 1 is some other constant b. So this is the ODE. These are the boundary conditions. All right, so for any problem of that type, here's what we can say. Oh, and also we're thinking of epsilon much less than 1, but greater than 0, as usual. For anything of this type, there's 3 cases that we can immediately say something about. If a of x is everywhere positive on this interval, and suppose it's strictly positive on the whole closed interval 0 to 1. If we have that, so it's case 1. And by the way, what's this a? Let's just stare at it. It's this coefficient right here. All right, the coefficient of the y prime term. If you want to think of it like an engineer or a physicist, if you think of the y double prime as kind of like, I mean, you could sort of read this equation as F equals ma for a weird kind of spring and mass and dash pot. You know, if you think of this thing as a damping term, kind of, and this as like a spring restoring force, you know, proportional to y. So y is a displacement of a mass on a spring. So this is kind of like it's got mass epsilon, it's displaced, its acceleration is y double prime. It's got some damping that is dependent on time, would be sort of the interpretation. It's a bit weird. This is my pet way to think about it. I like dynamical systems, so I'm used to thinking of my independent variable as time rather than space. So I kind of think of this as some sort of damped oscillator with a bizarre time-dependent damping a of x, a of t, you might say, and some weird spring constant that is itself not a constant, but is a b of t, a time-dependent spring constant and time-dependent damping. Anyway, if the damping is everywhere positive, so it acts like an ordinary dash pot to that extent, then the system will have an initial transient. That is, its boundary layer will be at time near 0. So in translating back to X language, the boundary layer will be at x equals 0. So what this would mean in mechanical terms is, I mean, it's actually most helpful to think of just let A and B, these coefficients be constants, if you just want the intuition. Ignore their x dependence. Just think of these as a damping strength and a spring stiffness. Then if you take a mass that's attached to a dash pot and a spring, and if it's got very tiny mass, then if you've sort of, what am I trying to say? If I displace it from equilibrium, the first thing that will happen is it'll do some very rapid motion. Like I'm picturing a mass in a big vat of honey that has tremendous damping. And so when I pull the system away from where it wants to be, the first thing it will do is try to restore itself quickly, and it will damp out very fast. That'll all happen at the beginning. And then after that, it's sort of just going to be a matter, like basically when the mass is small, if you take fluid mechanics, they'll tell you when the mass is small, that's like Stokes flow. That's like a particle at very low Reynolds number moving in a viscous medium. And so the first thing that will happen is that the inertia term becomes negligible as the system adjusts its speed. And after that, the viscous force, which is this term, is going to balance the spring force. Basically, the spring will drag the thing through the honey at long time. And it'll be moving very slowly, oozing. So you can neglect, this term is truly small in the outer region. It's only in the initial region that you get a big acceleration, and that's matching against the damping. Anyway, this is all a lot of physicist and engineering speak. And if you guys are more inclined towards pure math, you could ignore all of this. I mean, this is a theorem. You could forget the physical interpretation if you prefer. Anyway, I find it helpful to think that way, but you may not. It helps me remember. So conversely, if the damping, if this A of X is everywhere negative, on this interval, then the boundary layer is at the other end. And finally, what happens if A has a 0 somewhere inside the interval? That's an interesting case. So if A of X is 0 somewhere, for some X0 between 1 and 0, then we can have what are called interior layers. So instead of a boundary layer, we have an interior layer, where some kind of rapid variation will happen in the neighborhood of that point X0. And we're going to talk about those in the next lecture and in maybe a lecture after that. So we'll get to that. That case is harder, but so stay tuned for this, but not today. Okay, so I'm not going to prove this result, but if you want to look at this in more detail, you can see example 3 in Bender and Orsag on pages 422 to 26. They discuss this. So that's all I want to mention about that. Is there any question before I move on to our last example, which is to show that boundary layers can have thickness other than epsilon? So nothing about that? Okay. All right, so let's do one last example, which is how can you get a different thickness? So I guess this is example 2 now.
Sorry, I thought of a question.
Okay, sure.
For the A is completely negative case,
yeah,
I've always wondered what's the physical interpretation of that? It's like the opposite of damping somehow.
People refer to negative damping. The opposite of damping is pumping. So instead of dissipating energy by sucking it out of a system through friction, you're actually pumping energy in through some semiconductor device or something that is a source of energy. So like in the van der Pol oscillator that we'll be discussing at some later time, that's a famous nonlinear oscillator. At high amplitude, it has positive damping that tends to pull its amplitude down. But once its amplitude gets too low, sort of like a pendulum clock that's starting to damp out, there's some active force that pumps it back up. And so that tends to cause a system to have a self-sustained oscillation of some intermediate amplitude. So that's the idea. So negative damping you should think of as pumping. And it can happen. You can, like in the van der Pol, it's a nonlinear inductor that has that property. And nowadays you would use a semiconductor device to do that in electronics. In a mechanical system, it might be an escapement mechanism in a pendulum clock that gives the thing a jolt every time its damping gets too low. There's some gear or something hits something that pumps energy back into the clock. So that's an ancient idea going back to the era of Christian Huygens in the 1600s, how to make pendulum clocks that will run for a week, or something like that. Okay, but anyway, so here we are. Yeah, thanks for that, Jackson. That's a good question, though. So now, boundary layers of thickness other than order epsilon. So here's a little example of such a thing. This is copied out of Bender and Orsag from page 438. It's Bender and Orsag example 2. If you want to read their treatment of it. So here's the equation. Epsilon y double prime plus, so we've just been mentioning this A of X term, the damping. Let's suppose it has the form X squared. times y prime minus y equals 0. And, it'd be, okay, I want to continue with this, but it's occurring to me that everything we're doing here is so mathy with no science. And I'm actually a very applied person, and I like connections to physics and biology and everything else. So I was thinking maybe I should do a boundary layer calculation or two for you in the coming lectures that shows you where this would come up in some part of science. So it won't teach us a new mathematical technique, but how about I do something like that? I mean, if you really don't want me to, I can just stick to methods. But would you like to see? I mean, it's up to you. My feelings won't be hurt if you'd rather just see more methods. But I propose to do an example from biochemistry. Yeah, so I think I'll do that. I mean, the math of it is not very interesting, honestly, but the application is pretty interesting. And there are some interesting issues with how do you figure out what the correct small parameter is. So that comes up in real life. So yeah, I think I'll do that maybe in a few lectures from now. Okay, but not too much. I mean, mostly I'm trying to teach methods in this course. That's why it's called asymptotic and perturbation methods. but yeah, we'll do an example or two. Anyway, all right, so back to this problem. There's our ODE, and let's suppose we've got boundary conditions, which are, so the first one will be y of 0 is 1. And the other one will be y of 1 equals also 1. That's my second boundary condition. And so this is a little bit funky because of that x squared term. I asked Mathematica to solve this one exactly, and it couldn't do it. So that was interesting. I may not be doing it correctly. I even asked it to solve it asymptotically, and it couldn't do that. So that was interesting to me. When I asked it to do asymptotic desolve, couldn't do it. Again, I may not know what I'm doing, so maybe you can get it to work, but I couldn't get it to help. So we actually have to use our brain on it. Now, what do we think is going to happen in this problem? So you might notice it has something a little bit bizarre. Not terrible, though. This has an a of x equal to x squared, which shows that the a of x is positive for x greater than 0. However, a is equal to 0 at 0. So you might be a little worried because the criterion I just gave a minute ago said that I wanted a to be either strictly positive or strictly negative on the whole closed interval. Here, it's violating that at the left endpoint where it's 0. So I don't know, that might make you a little nervous, but it really shouldn't. I mean, this criterion of a being positive says that the boundary layer would be at 0. The fact that a is vanishing at 0 suggests maybe there's some kind of layer happening at x0, but that's 0 anyway. So something's happening at 0. So I think we're on pretty safe ground to assume that this is correct, even though it's not strictly true. So let's guess that there's a layer at 0, and that will turn out to be correct. Right. So we don't know how thick it will be. So let's do our usual game. So the outer region, well, then we would ignore the epsilon y double prime term, and you'd get x squared. And let me suppose I'm only doing this to lowest order. So I have a y0, and then that prime minus y0 equals 0 would be my ODE in the outer region, where I'm thinking of writing my y outer as y0 plus some order epsilon, correction that I'm not going to bother with. And so I can solve this little differential equation by separation of variables. I'm going to get dy0 over y0 equals dx over x squared. And so integrating both sides, you get natural log of y0 is -1 over x plus a constant. Let me call it C1. And then now, if I exponentiate both sides, I'm going to get y0 of x equals e to the -1 over x times e to the C1, and just call that C2. It's another arbitrary constant. So I have some constant times e to the -1 over x. And my boundary conditions, well, I'm in the outer region. I think the layer is at 1. So I'm going to impose the condition at x equals 1, because that's safely in the outer region. So y0 at 1 is 1. Tells me that C2 e to the -1 is 1. So it's giving me C2 is equal to E. And so I'm believing at this point that y0 of x is e to the 1 minus 1 over x as my outer solution. Let's see, there's a question or two in the chat. Oh, okay. People are saying it sounds like fun to do an application for a change. Good. Okay. Yeah, it will be a change of pace. I'm up for it too. I don't think I'll be doing it in the next lecture, maybe 2 or 3 lectures from now. Okay. Because actually next lecture, I want to talk about what happens at an example of when there's a point in the interior that can be a layer. We'll look at a phenomenon called a corner layer, which is kind of cool. But maybe I'll do it after that. Anyway, so there's y0. That's the outer solution at lowest order. Okay, now for the interesting part, which is that the inner region, I mean, the reason I'm doing this is I want to show you can have a boundary layer of thickness other than order epsilon. So let's see what happens. Let's let x be delta times big X. That's our usual move, written a little bit strangely, where here we're thinking of the delta as much less than 1, the big X is order 1 in the layer. And this is as epsilon is going to 0 from the positive side. Okay, so what's our equation? Doing the kind of games we did earlier, the ODE will become, let's look at it again. Here it is up here. This is our problem. Right, so we're still going to get that first term to be epsilon over delta squared, y double prime, or y sub xx. And plus, now x squared will become delta squared, capital X squared, and then there was supposed to be a y prime, which is a 1 over delta y sub big X. And the last term up here, so I've just written down this term, the x squared y double prime. Now I'm writing minus y. So that's minus big Y. That's all 0. Okay, so now let's clean this up a little bit. I mean, notice that there's a couple factors of delta here. There's a delta squared and a delta. So in fact, the scaling on this term is just order delta after you cancel out one of them. And so when we look at the balances, since I'm getting a little low on time, maybe I'll just say, you can consider, the three possible balances again. And what you'll find when you do that is that the consistent and non-trivial balance is going to be when epsilon over delta squared balances a 1. Right, so I'm looking at, I've got this term. I've got to take into account this, which is order delta, because that one's in the denominator. So let me write them all down. Epsilon over, there's an epsilon over delta squared, here's a delta, and here's a 1 in terms of the prefactors. And so what I want is that the first term and the last term balance, and they're both much greater than the middle term. Because watch what this would do. If I do this, is this consistent? I mean, this would give me delta squared is of order epsilon, which means delta, the thickness of the boundary layer, is like the square root of epsilon. And that's consistent because that is much less than 1. Right? So it's consistent. Okay, so let's go with that. And so we're going to use a delta equals epsilon to the half. And so then let's let big X equal X over square root of epsilon. That's our unusual scaling here. But hopefully you see how it was motivated. And so with that in mind, think about what we want to do for our perturbation series. Big Y should be Y0 plus, now what? You're not going to want to write epsilon because you've suddenly got epsilon to the half in the problem. So you should write epsilon to the half Y1, then plus that thing squared, which will give you an epsilon. And so you're going to be expanding in powers of epsilon to the half. So here, epsilon to the half is the small parameter. The expansion parameter that we should be using. Hopefully that makes sense. And so with that choice, our governing equation, we can substitute back in for everything up here using this new delta of X over using a delta of square root of epsilon. And you end up getting, so I'm going to skip the steps, at order 1, I mean, actually, we could probably just read it off. Let's just look. Going back up here, how's this going to work? I've done a balance on the 2 circled terms in red. And with the balance I've made, how's it going to work? So, oh, I see. No, I didn't balance those 2. I balanced this one. This epsilon over delta squared, we decided, is order 1. This is order 1. But this term is delta, which has an epsilon to the half. So my governing equation is, let me write it down, is y xx plus square root of epsilon, capital X squared, big Y sub x, minus big Y equals 0. That's my inner equation. Right, so there's no approximations yet. We just did a rescaling. So that's my inner equation. And now at order 1, I just read off this term and this term, when I do my perturbation theory, and ignore this one because this comes in at the next order, at square root of epsilon. So the order 1 problem is y0 sub xx minus y0 is 0. And I've got a boundary condition on it, which is that, remember, we decided there's a boundary layer at 0. So I impose that, I'm in the layer now, so I impose that boundary condition. Y0 of 0 is 1 was the condition. So solving all of this, you get y0 of x, capital X here, is a e to the big X plus b e to the minus big X. And that's kind of interesting because, well, let's see. Remember, we have to match this, what's happening in this inner region, to the outer solution. And notice this bad looking term right here, exponentially growing term. Really, I ought to determine the boundary condition immediately using this. But let me do things in a strange order, which is to say, I want to eliminate this exponentially growing term because I know I'll never be able to match it. I mean, I could just say, there's no way of growing something. This, remember, I have to take capital X out to infinity when I go out to the end of the layer. So this is going to be exponentially big. There's no way that this little thing, I mean, this is all behaving like order 1 on this interval. That's not going to be able to match it. So I claim that with a little bit of forethought, you can see that a equals 0 will be needed for matching. And that makes my life a little bit easier because then I can just say y0 of x is b e to the minus x, and now apply the boundary condition. Y0 of 0 is 1, and that will determine that b is 1. Okay, so I've got that y0 of x, the I don't know why I wrote those parentheses there. Let's get rid of them. The inner solution at lowest order is just e to the minus big X, which already matches my y outer sub 0 of x, which, if you'll recall, was e to the 1 minus 1 over x, because as x goes to positive infinity, we're getting that this goes to 0, but also here, as x goes to 0, the y outer goes to 0. So these match in the overlap region, giving us a y match of 0 itself at this order. I mean, they match in that they're both going to 0. So here's, I mean, I'm rushing a little bit because I want to show you a Mathematica calculation. So I have my y composite, which is y in plus y out, minus y match at lowest order is asymptotic to. So the y in we decided was e to the minus big X, which is e to the minus x over that interesting scaling of square root of epsilon. And then the y out is plus e to the 1 minus 1 over x, and the y match is 0. So there's my formula. And then the whole thing is plus the next order, which I didn't calculate, which will be square root of epsilon. So this is what we expect. And now this is the lowest order uniformly valid approximation. according to boundary layer theory. And so let's see if it's any good. But before I show you the numerics, I want to make one comment, which is Bender and Orsag make also, and it's interesting, which is that suppose we wanted to go to the next order of approximation. You don't need to, as you'll see, for a lot of purposes. But if you did want to go to the next order, like to estimate the error in this lowest order, that's one reason to calculate the next term. So if you did want to go to the next correction term, to YC, to the composite solution, you're going to need the order epsilon terms in the outer solution. Because remember, the outer solution was expanded in powers of epsilon, not square root of epsilon, right? The outer solution was just an ordinary regular perturbation in powers of integer powers of epsilon. So you would need the order epsilon terms in Y out, which would mean that you would need one more term in the outer. But the interesting and maybe a little surprising thing is that you're going to need two more terms in the inner in order to have any hope of doing matching. Because you're going to need to get the order square root of epsilon and the order epsilon in order to have a match. So the point is that the inner expansion requires twice as much effort as the outer one if you go to higher order. Takes twice the effort. So Bender and Orsag worked that out in detail, and you can check it out on page 438 to 441 if you want to see how that goes, with some interesting higher order matching of the type that we talked about in the last lecture. But I'm going to skip all that and just show you how this looks numerically. So let me stop sharing this screen and I will share this. I'm sorry I'm going over time. So close that. And here's my Mathematica done for you fresh this morning. Is that big enough to look at? I guess so. I'll make it even bigger. All right, so here's the outer solution that we just calculated. Here's the inner solution to lowest order. Here's the asymptotic, the composite solution where the match is 0, so I don't write it down. And now let me show you what happens when epsilon is 0.02, which I chose because it's big enough that you can see the curves being different, the exact and the approximate, but it's small enough that it works pretty well. So here I crank what I consider to be the exact solution by doing it numerically. God forbid the math department would see me saying that. But it's the closest I can come to an exact solution because Mathematica couldn't solve it. So it's a very high accuracy numerical solution. And I also plot our asymptotic solution, and this is what we get. So you can see we're doing pretty well. The blue curve is the numerical, the orange curve is the asymptotic. It's working pretty well over the whole range. It's, it's a little bit off in here. I made it on purpose to be a little bit off. If you wanted, I could, if I, like when I made them 0.01, rather epsilon of 0.01 instead of 0.02, I couldn't see the difference. But the other thing that I think is sort of interesting is to see what a thick boundary layer looks like. So this is what it looks like if I graph the inner and the outer separately. The outer solution is shown here in orange. The inner is in green. And look at, although it's decaying, it's taking its time to decay. This is what it looks like when you have a big, thick boundary layer. And so together they end up making this, when you add them up, you get a very good approximation to this blue solution as I showed above. But that's what a thick boundary layer looks like. And it's because square root of epsilon gives you a big thickness. All right, So I've taxed your patience too long. Thank you. And I'll see you next time.